Hi everybody, I hope you're doing well. This is going to be the last video for week 1 of distance learning in grade 11 physics. We're talking about Newton's third law in this video. First of all, welcome to my basement. Just thought we'd get out of the kitchen and living room for a little bit. Spend a lot of time in the basement these days because, as you may see, it's an unfinished basement. So we got some concrete floors where I can bounce my basketball, and I've behind me you might see the little the kind of hoop I set up. It's like a 6-foot hoop. The ladder there, so I can still practice. Oh, I missed that one. Let's get it in this time. Uh-oh. There we go. Still practicing my jump shot a little bit. And I want to show you a few things about Newton's third law down here as well. First of all, you'll see on the screen here the statement for it. The first statement is kind of a very simplified version. It says, for every action, there is an equal and opposite reaction. And you may see that in a lot of textbooks, or that's just what people might say when they say Newton's third law. They're just being a little bit lazy and leaving out a few details. The second statement there has some more of the details. It says if object A exerts a force on object B, then object B exerts an equal and opposite reaction force on object A. So it really emphasizes that Newton's third law deals with the two objects at one time, and I'm going to call them a pair of objects. And those two objects, let's say it's my two hands in this case, those two objects, every time there's a force, one object on the other, Newton's third law is saying that there's a reaction force the other way around. And I'm just going to bring your attention to the handout that you had from before the March break. We had a whole day where we talked about action-reaction pairs. And there's a bunch of examples there. Number one was a textbook at rest on a table. I'll talk about that again. And then pushing a box across a hallway. So that's what we're going to review today in this video. I think the simplest way to demonstrate Newton's third law would be to turn your attention to me pushing something. So I think I'm going to use this pole here in my basement, and I've actually strapped on my rollerblades for the first time since university. It's been a long time. Hope I don't fall down. Let's change the screen here. Alright, so I'm on my rollerblades. Skateboard would work better, but I don't have a skateboard, so rollerblades will have to do. So, I'm going to use my hands and apply a force on this pole. And what happens? Am I pushing the pole, or is the pole pushing me? Okay, so let's try. And there I go. So, I mean, the pole's not alive. I'm alive, the pole's not alive. I'm deciding what happens here, and I'm physically pushing the pole. So you might say Mr. Tang is pushing the pole, but the pole doesn't move. Okay? Actually, I move. The pole doesn't move. So then you might say, oh, actually the pole pushed Mr. Tang because Mr. Tang's the one who moved. Well, actually, both of those are happening. I push the pole, and the pole pushes me back. That's an example of an action-reaction pair. And the pole actually pushes me back with the exact same force that I pushed it with. So if I pushed with 50 newtons, I don't know how much I did, but if I pushed with 50 newtons, then I actually, my hands feel 50 newtons coming back the other way. Another way I'll show it is with a rolly chair that I have sitting here. I'm glad I didn't throw some things out. So, I'm going to push this. I'm going to give it a bit more mass. Alright, so put some water on there. So same thing, it's not a pull this time. This chair is going to move when I push it, and I'm going to skip down a bit to the level of the chair, well, as best I can, and let's see what happens. Alright, so you may have seen that the chair went that way, and I went the opposite way. I pushed the chair, but actually the chair pushed back on me with a reaction force. That's Newton's third law. Now I'm going to need the chair to sit on, so I'm going to grab it. Alright, you may have noticed that the chair moved a lot more, I guess, violently than I did. The chair accelerated a lot more than I did, and that's due to the mass. So Newton's third law says the number of newtons is the same. With me pushing the chair pushes me back with the same number of newtons. But since I have a much higher mass, my acceleration is smaller. You got to think back to Newton's second law, the last lesson. Acceleration equals force divided by mass. So mass is in the denominator. So with my mass being so much higher, that's why my acceleration is going to be lower. Okay, and that's the gist of Newton's third law. I'd just encourage you to look back into the notes from before March break to see some examples of action-reaction pairs. I'm going to just remind you of a couple. So here I've just got like a makeshift table here, and I got a can of paint, and I'm just going to put the can of paint on the table. Now, the paint can is at rest, it's not moving. And you may say, okay, so there's a force of gravity acting down on the paint can, and there's a force of normal that's equal in the opposite direction on the paint can. And you may be tempted to call that an action-reaction pair based on Newton's third law, but actually that would be incorrect. Okay, I just want to remind you that action-reaction pairs, they're only between two objects. So what I just described actually had three objects. It had the paint can. We talked about gravity, so that's the Earth pulling down, and that's the force of gravity, so the Earth was another object. And the table is a third object. We're not going to use three objects when describing action-reaction pairs. Okay, so gravity and normal force, they're not action-reaction pairs. What I can say is I can use normal force and normal force. So right now, the table has an upwards normal force on the paint can. The reaction force would actually be the paint can pushing down on the table. And I'll call that a normal force as well. So the two objects are the paint can and the table. Okay, one force is up, one force is down. It's an action-reaction pair. If you want to use gravity as your example for action-reaction pair, talk about the basketball here. So right now, the basketball has mass, so the Earth has a downward force of gravity on the ball. What would the reaction force be to that? So gravity from the Earth pulls the ball down. The reaction force would actually be the ball applying a force of gravity upwards on the Earth. So yeah, the ball is actually trying to pull the Earth upward. Just that the Earth's not going to move because it's way, way, way more massive than the ball. Okay, so that's another action-reaction pair. And the last action-reaction pair that I'll talk about that's most common would be like walking. And I guess I'm still on rollerblades, so I can't really show walking, but if I want to go that way, what do I have to do if I want to go that way? Well, I actually have to push back. Right? I gotta use my leg and push my leg, trying to force the floor backwards. And the floor is going to apply a reaction force on my foot forwards. allowing me to go forward. Okay, so that can be a third example of an action-reaction pair. And what I'd like you to do is practice that a little bit. Going to the textbook, which you're going to have to access online now. Just a reminder, the login information is on Google Classroom under the General Info section. And I just want you to try these 3 questions. And that will be a wrap for week 1 of distance learning. All right, so that's it. We'll see you next week then.